Oh, it looks like it's time. I think I was kind of just running out. Welcome back, everyone. For today's class, I don't have a ton of announcements, but definitely we want to talk about the exam. I intend to have this one graded by Friday, probably late Friday evening at the pretty much latest. In the worst case scenario, it might happen over the weekend, say Saturday. But once this exam's graded, I'm going to send a course-wide message just saying the grades are now posted. You can double check them in Moodle. And with where we're at in the course right now, pretty much I'm going to be updating your grades here on a not quite day by day basis, but on assignment by assignment basis. So every time you turn in a homework assignment that came due and I grade them, your grades will update here, and as well as your course grade is getting updated. So that means the course grade is calculated by doing this. At the moment, it's 30% for whichever homework assignments have been due. And because we only have one exam, I'm going to weigh the course grade after grading exam one, as it doesn't sound nice, but 70% is going to be the weight on exam one. That means it's just a best approximation of what your grade standing is right now in the class. And once you have two exams there, it'll be the average of that. Once we have the final exam, exams 1, 2, 3 will be the average of, will be 45%. So it'll start revising as we keep getting more and more grade components. But that's our intention for the exam. It'll be graded by Friday, and you should see the results posted on Moodle by Friday. Aside from that, we are nearly done with this problem, or this section. We have one problem to get through. But section 1.8, 1.9, that could have been just one really big section. Our author is just good at breaking things down. And so I feel like when we're going from here to here, we're doing almost exactly the same thing, just slightly more different terminology and topics in this section. Well, any questions at all, folks, about any of the announcements so far? You do, yes. I can back a hard copy for folks that show up in class. And for folks that can't quite make it each time, or if you just want it sooner, send me an email, and I'm not opposed to scanning it and just sending it right directly to you. I have a pretty fast scanner, so it's not a big deal. But yeah, I'd like to hand back the hard copies if I can, and a scanned copy if that's just the best way to get it back to you. Other questions about that so far? Okay, thanks for asking about that. Other things that I do after exam one's completed, once everyone in the class, I've graded their exams, like if there's an emergency and someone had to do a makeup exam, it could delay it. But once everyone has taken an exam and everything is settled, I post down here the solutions as well to the exam. So that way you'll have your original exam back, the graded one. You'll have the solutions posted down here so you can double check how each one of those problems go. And if I don't leave enough comments or the solutions don't describe well enough what happened on your problem, you're always welcome to ask me about it and we can look at it together, either after class or in office hours. Other questions so far, folks, at the moment? Okay, then pretty much what's going to happen on the Moodle website as we go to the next weeks is everything that we've done from week one all the way down, it just keeps repeating. So you can think of this as a brand new fresh start. We'll see assignments get posted down here. As we get closer and closer to this week, I'll start posting more information about exam two, the definite coverage, the review problems, and that kind of stuff. So we just get into a pattern that we repeat almost exactly as we go throughout the Moodle website. Well, it looks like we're about ready to jump in. Any last questions, folks? Okay, looks like we're in section 1.8, and here's where we left off. We're determining if we have a transformation indicated, say, in this format or in this format. We wonder if it's a linear transformation or not. Our first one, example 7, was pretty similar to a homework question, where we used this theorem. It's a very powerful and fantastic theorem, and it's a consequence of every linear transformation. It will always map the zero vector into the zero vector in its codomain. So if we test that out with this transformation, we're taking t of the zero vector, so here's 0, 0. Plugging those values in for x1 and x2 gave us that. We did not get the zero vector back like we should have. We got 4 in this component. And so we concluded that transformation is not linear on this one. I didn't ask anything too wild on the homework assignment, but example 8 is harder, and I felt like it'd be a good one for us to take a look at, just to practice with linear transformations a little bit more. So same kind of setup. It says transformation T is defined in this way. So it's going from, if it has two variables, let's see if we can re-specify this. It's going from R2, and we say R2 only because of the two variables. Looking at the right-hand side, we have two components. So this is a transformation that maps R2 back into itself. We're trying to decide if it's linear or not, but you might have already spotted a problem. That right there just doesn't look right. Even if you look at the first lecture, the first set of notes, if you had something that went x1, x2, and that's a weird order, plus x3 equals 0, this is not a linear equation at all because of the multiplication right here. So that tells us there's a problem, but we have to show why it's a problem specifically. So that's what makes this problem a little bit more challenging. To help us out with this, let's go and get some tools. If we're trying to decide if something is linear or not, really we should just be looking directly at this information up here. There we go. There's our definition for linear transformation. So let's bring this down into the problem. We can just squeeze it in right here. This problem, example 8, even though it's not in the homework set, it's kind of a preview. And this is a preview for 4.1. The portion that's a preview is this part right here, going for a counter example. This is a technique we'll look at again when we're in that section, when we're deciding if something is a vector space or not. Here the question is the transformation T linear or not? It turns out it's not linear. We have to show that it's not linear, and we need to find a counterexample that demonstrates it. So here's what we mean. If it was linear, this would always work each and every time. T of u plus v would be T of u plus T of v, and it would not matter which vectors you pick. U and v are fully arbitrary, it always works. If it's not linear, that means there's two potential problems. Maybe that equation doesn't work. If that's the case, we have to find a specific vector u, a specific vector v, that shows it breaks down right here. It's tricky though, because now for this transformation, part I might work, but there are transformations where part I would always be satisfied, and it's part 2 that's not satisfied. Linearity means both 1 and 2 have to always work, no matter what. So we're looking for one condition or the other that's going to fail. Sometimes they both fail, sometimes it's one or the other that fails. But this one is saying, if you pick a scalar c, and it could be fully arbitrary, and a vector u, any vector u, that should always work. Usually this is my go-to. We're told something's not linear, we have to show it. This one's pretty good to work with because it's a faster check. If it doesn't work, if we can't find a counterexample, you have to show there's two vectors where this equation is going to break down. So for the moment, we're going to show T is not linear by showing this is what's going to break down. But what we need is a counterexample. And so for our counterexample, here's how we're going to start. Let's maybe first say what we're doing. For a counterexample, we're going to let C be any real number, a specific one this time, and V, it has to be any vector coming from the domain, R2, but we're looking for a specific one this time. We're not trying to prove this always works. We're looking for one example that shows it won't work. We're looking at the transformation. You might not want to pick 0. You're just going to wipe out everything. As soon as you take 0 here, you're mapping the 0 vector. It will go back to the 0 vector potentially. And putting 0 here is just going to give you a 0 vector on the right-hand side. So sometimes we like to go something not too simplified. How about a -1? Reason for a -1 is, with these being multiplied together, there could be some complications with a negative times a negative resulting in a positive. That's going to show that equation breaks. So a negative sign right here might be a good choice, but it's not the only choice. There's potentially many counterexamples. Next thing we want to do is put down a vector here. And kind of the goal is not to work too hard. If you put in, say, 0, 0, that might not be a good idea for this one because you're just wiping out everything here. But if you put in a 1, 1, then that's not as bad. What I wouldn't do though is you wouldn't necessarily want to put a 1, 0. I'll delete this one in a moment. I wouldn't like that 0 because this is a 0 for x2. We plug in right here, and then we're removing the nonlinear portion of that. We just are going to get 0 in that component. We might never see why this equation's breaking. So because of x1, x2 being multiplied together, we want something non-zero in this location. And this is just a way to go. There can be as many counterexamples as there are people in the class, infinitely many different counterexamples. If this was ever an exam question, I would always try to make one that's really approachable. But there are hard problems where this might work, and it's the first equation that fails. We're not going to try to do those in exam settings, so that takes a while to just come up with something that would be the proper counterexample. Well, now that we think we have a counterexample, we have to show it really is a counterexample to equation 2. That means we focus on both parts. Let's focus on the left using blue first, and just see what that comes out as. In the middle, we're trying to break equality, so our hope is when we calculate the portion in green, we get something different. If we get the same thing, don't worry about it, just change your counterexample and find something else that's going to break that equation. Something will work. So next step, let's take and evaluate t of c times u. We also probably want to decide what notation do we want. It's written all sideways here. We stayed with it here, but because we're dealing with a counterexample, let's maybe convert our notation to a vector format. We did that. This is t of c times, oh, and I should put in the actual value of c. We chose for c right here to be -1, so let's plug it in. Our vector here is 1, 1. And we know it's not linear, so we're not going to move that negative sign out. We're trying to show that it doesn't work. So we're following order of operations and working inside the function statement. So we have t of -1, -1. That's going to output a 2 by 2 column vector. And I should eliminate that blue right there. Sorry, that color coding no longer makes any sense. Think of the first component being your value for x1. Second component is your value for x2, plugged in this kind of way. So for row 1, it's going to be 4 times -1, so -4. -2 times -1, so +2. And we get a -2 altogether on that one. Same song and dance. -1, -1 are going in here for x1, x2. That's just a +1 when they multiply. And that's our result right there. Any questions, folks, with evaluating the left-hand side? Okay, well, that was so fun. We'll just do it all over again on the right-hand side. On the right-hand side, we're looking at the scalar c times t of u. Let's plug in our information. Our counterexample says c is -1, so negative goes here. This is t of, oh, I'm writing down u's here and here, but that's clearly not a u. Let's see if we can fix that thing. Sorry for that weird notational. I think I know what happened. I indicated a v, but I started reading the actual statement here and I got conflated with u. Sorry, that should have been one or the other. Let's keep it a u. So 1, 1 would go here. Now we're going to leave that scalar just where it is. We have to do the mapping first this time. So negative just copies in. And now t is mapping 1, 1 in this particular way. You're just plugging ones everywhere now. So it's 4 minus 2 in the first component, or 2. This is 1 times 1 in the second component for a +1. And now we do the scalar multiplication. It's looking grim, except when scalar multiplication applies, it rescales both entries. So we're getting -2, -1. That means we have exhibited a counterexample. These are not equal at all, and we can give a conclusion that goes like this. T of c times u is not the same as c times t of u. We exhibited a difference in the second component, and this means, let's write, therefore, T is not linear. That deserves an exclamation mark because note, all we looked at was part two. If you show one part fails, that's all you ever have to do. We don't even care about what happens here. It might be that that always works. I doubt it, but we're not worried about it in this problem. This was the only counterexample we needed to show linearity absolutely does not work, and it's the multiplication here that broke it. Any questions, folks, with working with the counterexample here? Okay, when we're in chapter 4, like I mentioned, this is kind of a preview problem mostly. We'll come back to this kind of material and think about counterexamples again, since we'll have a few problems where we will do counterexamples as part of the homework and a potential exam question later on. But for the moment, think of it as we're just studying linearity a little bit more, and we'll come back to this idea in chapter 4. Well, we did it, folks. This is the end of the chapter 1.8, section 1.8 notes. I did have additional problems right here if we had extra time, but I feel like we probably are better served moving into the next section. However, if you're curious about any of these kinds of things, if I put this here and you would like to see it solved, just let me know anytime, in class, by email, after class. And I'm not opposed to running through these. I think these ones are actually kind of fun in a way. But let's save this up. Now we're going to go to section 1.9, which will be our last section of chapter 1. After that, we'll be getting into matrix algebra in chapter 2. Okay, so back to linear transformations. This time we're studying the so-called matrix of a linear transformation. However, we've already looked at that once in the prior section. We noted when we have a transformation that's linear, we can often write it this way. That doesn't always work. It's dependent on the vector spaces we're dealing with. But if your vector space is Rn to Rm, it does always work. A linear transformation will always be in this format for those kinds of vector spaces. However, change the vector spaces and all bets might be completely off for this kind of stuff. First thing I have here on the introduction of these notes are the theorem we used in chapter 5, the definition of linearity, and now notice, if you can write T of x as A times x, part 1 of linearity is just this algebraic property of matrix multiplication, matrix times a vector. Part 2 is a consequence of when we have a scalar times a vector, we can let the scalar commute out, matching that format. So in other words, if T of x is A times x, A is the standard matrix, and T is automatically linear as soon as it's written in that format. So that's what we're going to do right here. When you see a problem that says show T is linear, you could ignore this box. It's probably a bad idea because then you're using both of these definitions and you're not using a counterexample. You have to show this works for all arbitrary vectors U and V and all arbitrary scalars C down here. So that's a now honest, rigorous proof at that point. However, this is the way to get out of doing any of that. It's the way to work a little bit smarter and a heck of a lot faster. And that's what we're going to do on this one. We're going to prove linearity of this transformation just by writing it in that format. Once it's there, we'll just say, therefore T is linear. Any questions before we begin? Okay, really what's happening in example 1 is, it's just a review of our notation, matrix or vector addition, scalar multiplication, and how linear combinations result in a matrix times a vector. We take all this and write it in our more standard notation. It can be better shown. Oh, let me fix the pen here. It's a little bit easier to work with this if we bring in, oh, that is the right setting. That was weird. Sorry, pen's acting strange today. Let me collect my thoughts on more. Okay, the sideways notation's nice if you're saving vertical space, but it's not so nice if you're trying to show how the actual algebra is going to work with these column vectors. So we're going to convert this to T of x1, x2, x3. x1, x2, x3 maps to this, but let's write this out a little bit more carefully. It's in row 1. Let's carry this in, 2x1 plus x2. For row 2, negative x1 plus 5x2 plus 3x3. When you write these out, you want to try to do your best to keep these all arranged in a column for x1, a new column for x2, and so on, because those are going to turn into our column vectors. Last one, 4x1 minus 2x2 plus x3. So that's the whole mapping. Really, we didn't do anything, right? We just took this and wrote it in a vertical format. But now we can break this down. This might remind you of parametric vector form on our next statement. I'm undoing vector addition, scalar multiplication, 2 steps all in once. But it goes like this. Write down x1 plus x2 plus x3. Then, much like finding a parametric vector form, we pull all the x1 coefficients and collect them right here. So this will be 2, negative 1, 4. For x2, we're going to pull in 1, 5, negative 2 from over here, rather. And next for x3, being careful with the 0, we'll start with a 0, 3, and a 1. So now what we have right here is a linear combination. But any linear combination can now be re-expressed as a matrix times a vector. So now we've got, let's use a different color to make this pop out a little bit more. We've got a square matrix where we can pull in column 1, 2, 3 from just around here. So it goes column-wise, 2, negative 1, 4, 1, 5, negative 2, 0, 3, 1. This is multiplying x1, x2, x3. And this means at this stage, we just showed that t of x, this works for all x. We didn't use a specific example. We worked perfectly arbitrary. x1, x2, x3 are unspecified, but all of it emerges as a times x again, where x is x1, x2, x3, and this works for all x in R3. That means we're done, folks. We just showed that t is linear, and we did even more. We found the standard matrix of t. Knowing that matrix right there is going to allow us to say a lot of interesting stuff about what the transformation t can achieve. Things along the lines of, is it 1-to-1 or is it on 2? But let's put down our conclusion. We can now say, therefore, t is linear. And this is working fast as possible. Some of these algebraic steps might be kind of second nature to you from doing them repeatedly in the homework and such and studying. So if you skip from, say, here down to there, that's appropriate even on your homework. But if some of this algebra looks a little weird, it wouldn't be a bad idea to practice it on the homework just to get the extra experience with it. Any questions at all, folks, with example 1? Okay, here's some actually new information next. If we know that the transformation is linear, I scrolled not quite far enough, then we can just form the matrix A automatically. We take t of E1 for the first column, t of E2 for the second column, all the way to t of En. But then this begets more questions, right? What is E1? What is En? Let's go backwards. I forgot I injected this right here and deal with a little bit of notation. This notation is common. It's also very pivotal. And so this could be a really fast concept question even on exam 2. It says the identity matrix in Rn by n is indicated by sometimes just simply I if the context tells you that size, or we might say In if we need to specify the number of rows and columns. We don't say n by m because it's always from that space of matrices. So in other words, identity matrices are always squared. Here's how we define it. The main diagonal of an identity matrix consists entirely of ones. The off diagonal is of zeros. If we want to specify it this way, here's where we're defining E1 through En. EI is a column vector containing 1 in the ith row, 0 elsewhere. There's a lot to unpack there, so let's show how this goes on this example down below. First, if we write out I2, we could first indicate it by, it's the matrix with E1 E2 for its columns. Then if we really want to write it down, this is really the end step here. E1 has, let's see, EI is the column vector containing 1 in the ith row. So E1 contains 1 in the first row, 0 elsewhere. E2 will contain a 1 in the second row, 0s elsewhere. And so it'll look like that. So that's our 2x2 identity matrix. One thing that's special about these kinds of matrices is we've encountered them quite a lot, actually. Let's go back down memory lane and show where we have seen an identity matrix. This would be probably in section maybe 1.2. In section 1.2, we did some row reductions. And let's see, maybe not that section. Let me try again. We did row reductions here as well. And somewhere here, I know there's an identity matrix. There it is. That's our identity matrix right here. Sorry, participants, will move you over here for the moment. Now, this system was consistent. It had no free variables, so it also had the unique solution, 3, 1, -2. We just didn't write it as a vector at this stage of the course. But whenever you have a unique solution, you will exhibit an identity matrix in this kind of way, as long as you have same number of rows and same number of columns, of course. So we see identity matrices a lot when the columns are linearly independent, there's no free variable here, and that kind of stuff is where identity matrices show up. So there's our first one. Let's write down another one next, but first, any questions, folks, at the moment? Okay, let's go for I3 next. For asked to write down I3, the thing in the middle is not necessary. That's just us getting used to what are these objects. But let's write it in there just for that practice. I3 goes E1, E2, E3. Then it goes 1, 0, 0, 0, 1, 0, and 0, 0, 1. If you look at those columns really carefully, notice there is a pivot in every row. That means, well, this is an interesting system. You can say I3 times X equals B is always consistent. So that you can always find a solution to this. So if we have a pivot in every row, that's theorem 4 telling us this is always consistent. The columns will also span R3. So we can say span E1, E2, E3 is R3. And all this information from here to here, this is theorem 4 working for us. But this is a square matrix, so we can say even more about this. There is a pivot in every column. That means I3 times X equals the 0 vector has only a trivial solution. So that's kind of interesting, but it says something about the columns. They're also linearly independent at the same time. So we'll say here, the columns are linearly independent. I don't think I quite, well, I think that did just barely. So we have, for these kinds of matrices, not just the identity matrix, but it's one that satisfies it, it both spans and columns are independent. This is what we're going to say later on in chapter 4. E1, E2, E3 is the standard basis for R3. And it's a basis because we found linear independence of those columns, and they also spanned the entire space of R3 itself. We're extremely interested in those kinds of bases, and we're also interested in bases that are not as nice. Sometimes we want to change the basis, take advantage of other properties of the system. So we'll see different kinds of bases in chapter 5 when we're dealing with eigenvalues and eigenvectors. But really all the stuff we've been doing in chapter 1, it's the background for every single thing we're doing right after. So we review chapter 1 a ton as we go forward. Well, any questions at all, folks, with the notations or examples here? Yeah,
So in the, say the current E1 is a column vector, I think E1 in the height one, or I didn't understand that one.
yeah, I was saying a one in the ith row. So say, for example, E2 would have a one in the second row is what it would say here. So E2, let's write this one out for E2, has a one in the, we'd say at ith row if I is arbitrary, but if we're dealing with two here, we'd just say the second row. Does that make sense there?
There is also contained the I3, E3.
Exactly. So E3 will have a one in the third row is what that's referring to there. Yeah, it's kind of just weird verbiage whenever we're dealing with EI as arbitrary, going from one to n, they specify as ith row in that way. Other questions about that so far? Okay, so we've got this down. This is stuff we'll see quite a lot. And now let's ignore that for just a moment. There's trigonometry here for some weird reason. Let's focus on this for now. Theorem 10 says, if you have a transformation, this part's important. And that's why there's an edit on these notes. I need to specify t is linear for us in order to do this part of the problem. So if you know your linear transformation, let me try again. If you know your transformation is linear, then it will have a standard matrix if it's going from Rn to Rm. And all you need to do is evaluate like this. Take T of E1, the first column vector in the standard matrix. Column 2 will be T of E2, T of E3 for column 3, and so on, all the way to T of En. This is a process we'll use when we're doing some of the homework questions, I think 1, 2, and 3. But I think a good way to show how all this works is example 3 right here. What we're going to build in example 3 is a formula. This is an actual example in the book as well, but I felt like it's kind of foggy how the author actually put that all together. So we're going to do it ourselves, build it from scratch. And let me put a note here. This will be helpful for the homework. Let me be more specific. In the homework set for assignment number 8, problems 1, 2, and 3 are just using that theorem that we're indicating, but we're doing a formula that's going to help us on exercise 3 in section 1.9. So let me put here homework number 3. So let's look at what T does. T is the mapping that rotates every vector in R2 clockwise. That means we're using a positive angle for rotating that way, about the origin through the angle theta. This is a linear transformation if all of it's doing is rotating every point in a rigid way. So we should be able to find its standard matrix. Here's how we're going to start. That's what the standard matrix will look like. So we'll begin by putting down a plane to represent R2. Here's where E1 is. As a column vector, it would be 1, 0. And E2 would be here. As a column vector, E2 is 0, 1. But same exact stuff as we looked at when we were up there looking at the notations. So that's where they start. Next thing that happens is the transformation T gets involved. So I'll indicate, here's the domain space, R2. It's getting mapped back into R2. And we're rotating by an angle theta, clockwise. It wasn't specified the rotation, but I'll make it an acute angle, just so it's easy to draw and see where everything is going. So here's E1. Let's say it rotates by roughly what looks like 30 degrees. Doesn't have to be exactly 30 degrees. So E1 ended up here. Now it's over here, and this is T of E1. We need to find out the exact coordinates of this, and some folks might know right away. Anyone happen to know what that coordinate would be right here? Not necessarily, because T is taking this right here and rotating it to a new location somewhere right around here on the plane. but it wasn't meant to be exactly 30 degrees, just drawn to be kind of about right there, just to make it an easy sketch. It has to be an arbitrary angle rotation that we took. But there is a hint to this. Here's the hint. E1 is a distance 1 away from the origin, and so is E2. They lie on a unit circle. So if you put a unit circle through here, then by the definition of unit circle trigonometry, the coordinates on this spot are exactly cosine of theta, sine of theta. I feel like that comes out of nowhere, but this is now review of trigonometry coming into linear algebra out of nowhere. Does that make sense, folks, on getting that T of E1 right here? Awesome. It's a little bit more tricky because E2 is rotating to about right here. Let's show it on the diagram. Here's where T of E2, well, let me try to make it about 30 degrees. Maybe right around there. That's where T of E2 ends up. And T of E2 is a little bit harder to specify because there is more than this rotation of theta. So let's put this in. And I'm just trying to find a color that's going to stand out. Let's go with purple this time. So this short rotation is theta right here. But when we rotate from the positive x-axis counterclockwise to over here, we are also going this way. Let me see if I can point at that a little bit better. This is theta plus the 90-degree rotation from here to here, which is pi over 2. So theta plus pi over 2 is that rotation. That means at this point, this is where T of E2 lands. Looks like I should have made this all a bit bigger. Let me squeeze it in right here. Here's T of E2, and if we're going to specify it in this way, it still works, but it looks kind of nasty at first. T of E2 is going to be a cosine function and a sine function, just like before. But the angle is theta plus pi over 2 because we ended up way over here. That's not just theta as a rotation. It's quite a bit more. So cosine theta plus pi over 2 plugs in here and here as well. So we can assemble the standard matrix A right away at this stage. We have T of E1, that's exhibited right here. T of E2, the last one is here. But this is not a formula that's typically given. And folks who have seen this formula are probably kind of mystified. Where are all the sign changes going? Why does it flip from sine to cosine when it should have been cosine and sine? There's lots of weird things happening. That's finally where this stuff comes into play. We need this identity from trigonometry. I should say right away, this is never something that'll happen on an exam question. This is more us just seeing how linear algebra is going to work with this weird theorem. We're also going to need this identity from trigonometry. So let's display them down below here temporarily while we work this out. So cosine as a addition formula goes like this. It's going to be cosine of theta, cosine of pi over 2. Then I want to say plus, I dearly do, it feels right, but it's actually a minus. Trigonometry is just weird like that. So it goes minus sine theta, sine pi over 2. The addition formula for sine is a little bit more normal, except it goes sine, cosine, cosine, sine. It has a weird pattern like that. But plus at least goes to plus, so it's not as weird. So on the second row, we'll have sine theta, cosine pi over 2, plus cosine theta, sine pi over 2. That means we're nearly there, folks. We're just about to simplify all this down. The good news is cosine pi over 2 and sine pi over 2 are fast to calculate. And we recall cosine at pi over 2. Is that one a 1 or is it a 0? Good call. So that means all that's gone. Down below, so is all this. Cosine pi over 2 is 0. Wipes out those points or those terms. Over here, sine of pi over 2 is a 1. And so this turns into a negative sign that we carry in. So negative sign to this location. Like again, sine pi over 2 is a 1, so we get a cosine in this location. So now we finally mapped E1 into that vector, cosine sine. We're mapping E2 into this vector, negative sine, positive cosine. And that means we have the standard matrix. Scroll up here. By the red dot, this is all we need to do to summarize the whole problem. T of x equals ax, where, oh, not x, let me try again, where a equals, take your T of E1, plug in cosine theta, sine theta. Then take your T of E2, plug in negative sine theta, cosine theta. That's kind of interesting. You pick any angle you want. Theta could be pi over 2, it could be 1.5 radians, something really random like that. Then this transformation will rotate every single point in R2 by that amount by making this right here. Multiplying this particular matrix by your vector x, it will always do the right rotation. It's kind of weird, but that's an interesting linear transformation. And you can use this part as the formula for the homework exercise 3, the standard matrix there. Well, any questions, folks, with what's essentially, I guess, a derivation for this one? Okay, so the moment we know the transformation is linear, it's fast to assemble a standard matrix of A. We just take T of E1, T of En, and drop it in that way. So here was our T of E1, and this was our T of E2. Well, last topics we want to take a look at are information about when is a transformation T 1-to-1, when is the transformation T onto. So that's this mysterious page of the notes, so it has a lot of white space. I should mention before we get too far, if you studied mathematics out of different textbooks and different contexts, this has a different name that's used a lot. This is due to the French. The French kind of took over onto, and they call it surjective. You can use that in your homework if you like, but always use onto, since that's what our author is using. But if you've gotten into the habit of using surjective, you don't have to change your habit. Likewise, the French also have a different one for this one. They call this injective. I don't know enough French to tell you why it's called injective or surjective, but I just know that's what they call it. So that's surjective versus injective. And I think this is a good part of the notes to explain why in the world would we care about a transformation being onto and 1-to-1. Sorry, I almost used the wrong words. We don't care as much in this course, but we deeply care when a linear transformation is both onto and 1-to-1. That is something extra special in mathematics, and it's why linear algebra tends to show up in a lot of different contexts, like trigonometry, for example, just shows up out of nowhere. So down below, we'll take a preview. This is completely optional reading, but it's worthy to look at just a little bit if we're interested in what's going on with linear transformations. So it turns out, if you have a transformation that's linear, so it satisfies this right here, but it's more than just linear, if it also satisfies, say, 1-to-1, if it's also onto, it's what's called an isomorphism. In mathematics, isomorphisms are extremely special. Let's break down that word. Iso meaning same, morphism means form. Might be Latin or something, I'm not completely certain. So you'll see the words isomorphism a lot the more mathematics you take, just meaning something has the same form. And it turns out the field of complex numbers is isomorphic to matrices of this form. You could work with those matrices exclusively, and you're working on complex numbers. But another way to think about it is, for this quick example here, suppose an American and German are asked to count a handful of objects. We would say 1, 2, 3, 4, 5. In German, if anyone speaks German, let me know, and I will save the trouble of saying this wrong. The German person will say eins, zwei, drei, vier, and fünf. but they're both doing the same thing, right? They're just counting things. There is an isomorphism between what the American is doing and what the German is doing. Likewise, if we say 2 + 3 is 5, the Germans will say zwei und drei ist fünf. They're doing the same thing. It's the same exact concept. Just looks different, right? There's an isomorphism there. And there was a lot of drama in mathematics back in the day, if you're curious. This gentleman, Cayley, in 1854, people wanted to murder him. He completely threw this theory of mathematics on its head. Back in the day, group theory is a field of abstract algebra. It was its own thing, and people were very proud of group theory, what it did, they could work on with it. And there was another school of thought. Some people worked on groups of permutations. It looks absolutely different. It doesn't look like compatible mathematics at all. But Cayley came around and he found an isomorphism between two branches of mathematics. He showed that everything people were doing over here in the group of permutations, they really were just doing group theory. So all these people who had built a career and a reputation on groups of permutations just got told, hey, you're no different than this. It's just a different language. Your mathematics is actually the same as ours. Here's the isomorphism. So that's the role linear transformations can play. There's a lot of other reasons why we like them, but we can take different parts of mathematics and show, are they truly different, or are you doing a new theory at all? An isomorphism will say once and for all if the theories are actually just the same thing. But to do that, we have to get onto what is onto and what is one-to-one. So that takes us back here, back to injective, surjective, if you speak French. Any questions so far, folks, before we start tackling down these two definitions? Okay, I felt like before we get too far on these, let's just do a really fast example. Suppose you have a mapping F. Ordinary function, it's going to go from R to R. So these are the functions we're used to using in Calculus 1, Calculus 2, for example. If your function goes like this, f of x equals, let's say it's x squared. Then f is not onto. Let's see why. It says you have an onto mapping if each vector b, or each codomain element b, is the image of at least one x in Rn. The wording there is really tricky. It's almost easier to see it just by graphing this function. So let's do a really quick graph. And work through this wording right here with our graph. So our function is x squared. Now when it says, oh, this is a little tricky. If each b in Rm is the image of at least one x, the b in Rm is referring to a b in the codomain, so a b in R, and there are certain b's in R that we can't hit. Say, for example, this one. No matter what you plug into that function x squared, you're never going to obtain this value. That means -1 is not the image of at least one x in Rn. They're referring to the domain space. Take any x here, you never drop down to the -1, so f is not onto. Change the degree though, that one is onto. You can get to -1 easily. You just plug in -1 and it maps to -1, no problem. So this function, that's kind of weird with an exponent like that. But this function, oh geez, it's kind of ruined actually, there we go. This function would be onto. When it says b is the image of at least one x in Rn, the image you can have in your mind is every value on this axis has a pre-image, some value in the x-axis that maps to it. So let's say here, just to complete the thought, f mapping R to R, defined as f of x equals x, is onto. So that's the analogy. I think onto and one-to-one, they're kind of hard definitions. This is what you would want to think of the picture in your head as an analogy for what onto really looks like. And now we need to add even more information. Let me get rid of that first. let's bring this back to what we really care about. We don't care about an arbitrary mapping. We care about the ones that are linear. This is linear algebra after all. So let's retune this definition in the linear algebra way. Let, that's probably the wrong color. Let's go with green for onto. Let T map Rn into Rm. So we bumped up the domain codomain to honest vector spaces instead of the real line. And we're going to let it be linear. So now that we have a linear transformation, there exists. And let's double check this. This is Rn to Rm. So there exists an M by N, change the order there to get the right size, matrix A such that T of X, let's actually put it right here, T of X equals AX for all X in Rn. So all we did is we exhibited T is linear, we just set it by assumption, but then we can exhibit there is a standard matrix A that goes along with it, because every linear transformation will have that standard matrix, as long as you're going from that space to that kind of space. That means, well, if T is linear, let's also say, suppose T is an onto mapping. Now we're pulling in the definition above, and we're going to show what happens with the onto mapping with an honest linear transformation like this one. Well, let's go back to this. Each B in Rm is the image of at least one X in Rn. We need to break that down, and it's technical, so we'll go slowly. Let's say, let B be in Rm. Rm is the codomain space. Then T of X equals B is consistent. Let's explain this line right here. This has to be consistent because it says it will be the image of at least one X. There has to be an X, so the B is the image of it under the transformation T, meaning this just has to be consistent. But hang on, that's then consistent. A of X equals B is consistent for all B in the codomain Rm. That's because they said each B. That's like saying every single vector B has this property. So if we're always consistent, you might say, hang on, we just had an exam, and you might remember this really clearly from the last page on the exam. We're looking at theorem 4 all of a sudden. We have AX equals B is always consistent, always has a solution. We can now say something about the standard matrix of A. It will have a pivot in every row. And that's what onto means for a linear transformation. There's a pivot in every row, and that's fantastic for linear algebra. What we just did is we broke down something that is a very technical definition, even though it's a short line, into where are the pivots? That's what it all breaks down to. Let's come down here and say, this implies A has a pivot in every row. Sorry for the all caps, but it's extremely important to remember we're talking only about rows, not columns, when we say onto. Well, that's a breakdown, and this is the whole punchline. You can solve a lot of your problems that involve onto just by looking where is the pivots in the standard matrix A of that transformation. Any questions at all, folks, with this last punchline down here? Okay, so that's what onto looks like. A pivot in every row. It's just a reformalization of theorem 4 in a real sense. Now let's take a look at one-to-one. I think this needs a new page. Let's drop it down here. Should have done a whole page to start. So injective or one-to-one is kind of its own thing, but it's related to what we just did. Let's start off in the same kind of way. We're going to begin by saying, assume T mapping Rn into Rm is linear. So now we're only dealing with linear transformations. Looking here, it says, well, for any mapping, we'll say it's one-to-one if each B in Rn is the image of at most one X in Rn. Let's take a look at a couple pictures just to get a feel for that. This would be a one-to-one mapping. Let's see. B is the image of at most one X in Rn. The B they're referring to would be something out here. So there's your value B that they're referring to. And sure enough, it's the image of at most one X value. There's no other way to get to this value B here because the line is straight. You have to use exactly that. If there were two ways to get to B, we would have said that this is not one-to-one. But for the moment, that's our picture for a one-to-one mapping. Let's change it up a little bit. Bump up the power to power 2, and now we have a problem. I definitely have a problem. Let me bring that back. I was trying to do this right here. So let's run through the definition again. It's talking about each B in Rm is the image of at most one X. Well, there's some B's that you can pick, like say this one. This is not the image of any X because you can never go down that far. That's okay. That's not what's stopping it from being one-to-one. If you take a look at this B, that's where the actual problem is. Let me erase that other one real fast here. We wonder, how do you get to B? It's supposed to be the image of at most one X, but there are multiple ways. You could take this X value, goes up, and it maps to B. Let's call it X1 since that's one of them. And there's another X value right down here. Let's call this X2. It goes up, maps back to B. So this one is not 1-to-1. A related concept, people would call this one, it is 2-to-1. Because two preimages map to one B in Rm, in just R in this case. Kind of lost my words there, but any questions, folks, so far with what something not one-to-one would look like? Okay, let me take a quick screenshot on this one. Maybe just drop it there, and let's work now on these kind of transformations. So we want transformation T, we want it to be linear at the same time. Let's also assume it's one-to-one. Assume further that T is 1-to-1. Well, I wrote this in kind of a weird way. There's not much I can do with this. We need to go back to where we said T is linear. So let me put a statement that says, because T is linear, there exists an M by N matrix A such that T of X equals AX for all X in the domain space. This would be Rn. Okay, that's the whole point of this section right here, the standard matrix of the transformation. So definitely don't want to forget that. And also, I can't do anything with this information until we bring in that standard matrix A for the transformation. So now let's see what we're getting into. It says if each B in Rm is the image of at most one X, there is one B that is extra special, the zero vector. Let's use the zero vector in our next step here. And maybe let's ensure we can fit this all in one page. There we go. So let's say here, T of X mapping to the zero vector, it says is the image of at most one X. Well, we know it's consistent. because this is a linear equation. You can just put in the zero vector in here. It'll map right back to the zero vector. Automatically, it's consistent. And we should expect that because it's now a homogeneous equation with zero on the right-hand side. So it is consistent. We said that, let's see, t is 1 to 1. There is at most one x in Rn that would solve this. And so we can say it is consistent with a unique solution. I think the 1-to-1 case is a little bit more tricky, but the unique solution came from this, at most 1x. So that's helpful information for us. But we can't do a whole lot with that, right? We need to take t of x and throw down the standard matrix A in its place. So t of x is the same as A times x equals a zero vector. This line is only because t is linear. Now, back over here, we just said it has a unique solution, so we can say in different languages that ax equals a zero vector does not have non-trivial solutions. You can say a whole lot more about that then. You can say then ax equals a zero vector. If it doesn't have non-trivial solutions, it doesn't have free variables either. So let's say has no free variable. But what I'm really circling around, almost like Simon rolling into a concept, is not as much about non-trivial solutions, not as much about free variables. What I really want to say is something about the columns of A. Are these columns linearly independent or linearly dependent? Anyone happen to know? Sorry, say again. Exactly. If there's no free variables, or on this line, I kind of wrote it weird. You could rewrite this by saying it has only the trivial solution. But either way of thinking about it, columns of A are now linearly independent. So let's say that as our next line. This implies the columns of A are linearly independent. So linear independence has more to do with 1-to-1, it turns out, if your transformation is linear. Likewise, if we're talking about onto, there's a pivot in every row, that's about spanning if there's a pivot in every row. So spanning is onto, linearly independence is 1-to-1. That's kind of weird, but that's just how the definitions fall when we look at this. And we can do even one better. On the last part, we said the mapping is onto if the standard matrix A has a pivot in every row. Over here, we're going to say columns are linearly independent if and only if there's a pivot in every column now. That's our related concept. And we'll box out this statement. We'll say, therefore, there is a pivot in every column of A. And let's make that pop a little bit more, since it's very important to get rows and columns the right direction. If we mix them up, we're mixing up a lot of terminology. So there's a pivot in every column of A. So that's the major takeaway of that thought right there. Any questions at all, folks, with the work so far? In a certain sense, it's a whole bunch of review. These were the things we were tackling from section 1.1 all the way through section 1.7. Homogeneous systems of equations, non-trivial solutions, free variables, all culminates right down in here. And that's a lot of work we wrote down, but this is the big punchline. Theorem 11's nice. It says, if your transformation is linear, it's 1-to-1 if this only has the trivial solution. But in this class, people usually go to theorem 12 because it's paraphrasing even more stuff. T maps Rn onto Rm. In other words, T is an onto mapping. If the columns of A span Rm, and let's put our thought here. This means, let me make sure I'm going to fit that well. Let me try a little bit reformatting. Okay, the columns of A span Rm. Here's our paraphrase thought. This just means there's a pivot in every row. Likewise, T is going to be a one-to-one mapping, meaning the columns of A are linearly independent. These are if and only if, so the logic works both ways. The columns of A span Rn, if and only if. Let's put that next if and only if right here. There's a pivot at every row. And the columns are linearly independent if and only if, so a bidirectional arrow to say the logic goes both ways. We have to have a pivot in every column. So that's kind of amazing in a certain sense because it's good to remind ourselves onto and one-to-one are not easy definitions. You will work with them directly in other math classes, the more math you take. But if you're dealing in linear algebra, all of this technicality simplifies down to pivots. Just row reduce your matrix to echelon form. You've shown the pivots, and you can make powerful conclusions just based upon that information. Only if the transformation is linear. Take a nonlinear transformation, all bets are off. Anything can now happen. Well, any questions, folks, with the theorems 12 here? Okay, for the sake of homework, I'd say exams. The comment that we put here in pen, I'd say this is a powerful way to work these theorems. Let's show how it goes right down here on T. So T goes from R4 into, this is kind of a wild looking one. Let me see if I can organize this. It's taking 4 different variables. So T maps R4 into, let's see, there's 1, 2, 3, 4. So we're going from R4 to R4. These transformations are extremely special because observe for this transformation, your standard matrix is square. If there's a pivot in every row, there's also a pivot in every column. So for square matrices or transformations that go from one space into the same space, sometimes these are given a unique name. Linear operator, because it's domain space and a codomain space are the same. For linear operators, onto and one-to-one is the same exact thing, and that's kind of remarkable in a way. It all just delves down to the pivots, and lots of technical information about functions becomes really fast. Just look where the pivots are. And even faster, if there's a pivot in every row, there must be in every column for this matrix. First, let's get that standard matrix. We can reformat by going T of x equals x1 plus 2x2. Next entry is all zeros, so that's a little tricky. Then it goes 2x2 plus x4. This is now a little bit more about bookkeeping than anything else. In the homework, this is possibly a good strategy as well. When it says 2x2, you really want to put it here. Plus x4, let's go here and insert a 0 in the middle just to remind us that there's a blank right there. Next one is x2 minus x4, so let's go x2 plus 0. You know, let's maybe make that a little bit better. Plus 0 x3 can help us out. Plus or minus x4. And this one was plus x4. So there's our same exact transformation. This notation is not doing us any favors. It's just making it cheaper to print the book. This is what we want to view it as, because now we can say T of x is equal to this matrix times x1, x2, x3, x4. Now we're back to the thing that we did on day 1 of the class. We're already week 5, but same strategy. Pull coefficients. Big thing in linear algebra. Column 1 coefficients for x1 go 1, 0, 0, 0. Column 2 coefficients for x2 go 2, 0, 2, 1. Column 3 coefficients for x3 are all zeros. 0, 0, 0, 0. Column 4 goes 0, 0, 1, negative 1. So this is the standard matrix A, and that's the vector x right here. So we just showed that T of x is equal to AX, and this is always, but we expected that, did we? T is a mapping defined in this way. You know what? They never actually told us T is linear. We just showed it. Let's say here, this shows T is linear. I said they never told us it's linear. That's actually me. I never said it was linear here. That was my omission. But we just discovered it by exhibiting the standard matrix of A. Doesn't answer our question, but let's look at this matrix. There is automatically not a pivot in every row. The moment you have a zeroed out row, that's excluded. But if you can't have a pivot in every row, you cannot have a pivot in every column either. There's also a zeroed out column, but even if there was a 1 here, one zeroed out row is enough to say there's not a pivot in every row and there's not a pivot in every column. Let's say that right away. There is a 0 row. We're looking at row 2. You can make the same statement by saying there's a 0 column, column 3, and so not pivot in every row and every column. But just due to this right here, if there is a 0 row, there cannot be a pivot in every row. This automatically implies T is not onto. The moment we lost a pivot in every row, we lost onto on this transformation. It's doing something else. Then we can now say there is also, let me just move this over here for a moment. There is not a pivot in every column. Then we have an immediate conclusion. Lack of pivot in columns implies T is not 1, 2, 1. So that's kind of amazing. If we had to work with the definitions directly with this transformation, it's a lot of algebra. It's a slog, and it's not clear what we even did. It's a hard process. But knowing it's linear, this is all it boils down to. Where are the pivots? We didn't even have to do one step of row reduction to exhibit these two facts. Well, any questions at all, folks, about that transformation? Okay, well, we're not quite done with the notes. We have other exciting things that we're going to get into. I feel like this is a very good problem to look at. It's a source of concept questions. There's related questions in the homework. So we'll come back next Tuesday, finish off example 5. This one was if time permits, so I'll leave this one blank. Let me know if you'd like to see the solution, and I will upload it. It's kind of a fun one as well. What's going on here is, this might be the first example where our codomain is a vector space, but it's a function space. So, excuse me, that's the domain, and so is the codomain. C01 is the set of all continuous functions on the domain, the closed domain 01, and this transformation is in fact linear. So is the differential operator. That's a linear transformation as well. Any kind of questions that we ask or any theorems that we develop about linear transformations, it carries over to integration. That's also a linear process. So linear transformations are everywhere. Trigonometry, calculus, and so on. It just keeps coming up and coming up. That's why we spend so much time on delving into what transformations should look like. What do they do and what properties they have. Well, I think this is a good stopping point then for us, folks. Any last questions or comments before we call it an end? Okay, well, have a great night, everyone. We'll come back next class and review the theorems going through these examples below. You bet. Thanks for the participation, folks.